So let's begin. Welcome to class on this charming morning. The roads, most of you guys just walked here, but you guys know the roads were extra special today. Really gross. So let's see. Today, a little bit more from 18.4, and then we'll start 19.1. Homework help today, 3 to 4. Food systems talk, 4 to 5. Thursday, tomorrow, homework help 9 to 10, 3:30 to 4:30. Friday, homework help 3:30 to 4:30. And we'll continue with 19.1. We'll probably just kind of like get a preview of this, and then we'll get into 19.2 on Friday as well. Let's see. A couple people have asked. I'm not planning on any sort of final exam, but it'll depend how the next couple of classes go. The last assignment, I might include a few sort of review problems, nothing super difficult, but maybe a chance to review some of the stuff we did a long time ago. But it'll depend on where we get the next couple days. I think we're kind of ahead of things. So the last two homework assignments will probably not be, and they shouldn't be like off scale hard, but they probably won't be like short either. So they'll be good full problems. And so part of it is just the material from, we're going kind of quickly now, 18, 19, and 20. The material is, I think, a little bit harder. Personally, I feel it's also more interesting. There shouldn't be any super long calculations. That's not my intention for any of these. And then, like I said, if there's time, if it looks like it, we can get through what I want to get through in chapter 20, I may include a couple sort of synthetic review problems or something for the last problem set. Any questions? OK.
So
yeah.
After this week, there are 2 more?
Yes. So March 11 is the last day of class. Yeah. And then our spring term begins March 28, I think.
Spring term.
Spring term, yeah. Right, so you have spring break, but then spring term starts up March 28. So we have 2 weeks for our spring break. Yeah. OK. So last time I issued a warning that I was going to do more talking than usual. I'm not sure I actually did, but this time I really mean it. I'm going to do more talking than usual. I have like 2.5 pages of notes. So this will be a little bit of a long derivation, but I think it's and also a recap discussion of what we did last time. But I think it's worth. Obviously, I think it's worth doing. Otherwise, I wouldn't be doing it. So today will be a little bit unusual in that I'll be doing a derivation for a little while, and then like the first worksheet you have will just have like one little problem on it, and you'll do that, and we'll feel good, and then I'll go back to talking. So brace yourselves. Hopefully, this will be interesting and fun. So first, I wanted to remind us all of what we did last time, which was a variation of the fundamental theorem of calculus. So this says if you have a line integral, you don't necessarily have to do that annoying parameterize the curve and do the integrals and the dot products and so on. If it happens to be a gradient field that you are integrating, then no big deal. You just subtract the value of the function, endpoint minus starting point. And this then ends up not depending on the particular path you take. So that also gives one a great deal of freedom and flexibility. And let's see. So some notation. Let's see. A term I didn't mention last time is that if we have a vector field f that derives from a gradient field little f is called the potential or a potential function for that vector field. A warning, though. In physics, we like to get our vector fields, usually force fields, and we define it with a minus sign out there, because we like our fields, our arrows pointing downhill instead of uphill. And there's actually a reason for that, because that's the direction that force points. Force points down a potential field. So this would be phi from like the electrostatic potential. So anyway. Just yet again, physicists and mathematicians not quite getting along. Although this misunderstanding seems more understandable. Yeah.
So is the potential function, is that
is that the term potential in terms of like, well, it could be this, or is that saying potential as in terms of like electric potential?
Electric potential, yep.
Okay.
Yep. So if this would be, right, so in electrostatics, E is minus, or that's the electrostatic potential. Yeah. And in, this would be, I don't know what. So if this was a gravitational potential energy, yeah, then this would be the force due to gravity. Yep. And you're maybe used to seeing this, if at all. I don't know. Maybe not. Anyway, it's E is minus del phi. Has a nice Greek sound to it. OK. Let's see. Then there's this quantity, the scalar curl. And I think I might have defined it the other way around in class. Speaking of minus signs, it doesn't really, for the curl test, it doesn't really matter. And what we're going to do today is we're going to explore this quantity and sort of see why it's called the curl. You know, it's not some random thing. So then we didn't quite prove, but argued a number of results. So the following statements are equivalent. F is a gradient field. I guess I should say continuous. And if we know this, we immediately know a lot of other nice things. We know that f dot dr is path independent. For all C in some domain in which this is continuous. So that's nice. Just evaluate the endpoints. It doesn't matter how you get there. What about this? 0, yep. For all closed C. And this means, right, that this, just a reminder that this integral is called the circulation. And so this would be the curl test, a way to find out if there exists a potential function, a lowercase f. So I gave you that example, and you couldn't do it. And I said, yes, you're right, you can't do it. How could we have figured out in advance you couldn't do it? I said, this is the test you would sort of do. This is actually a somewhat important little bit of fine print. If you have a domain that looks continuous, but the origin isn't included because maybe you have a 1 over x term and you're dividing by 0 there, that then can sort of complicate this. But I don't think I want to go into that too much in this class. So what I mean by all these are equivalent is if you know one of these things, all the other things follow. Yep.
Does L'Hopital's rule work for that last one?
I mean, you could. I mean, if the function, if the vector field, you can use L'Hopital's rule probably like to patch up a domain where there was a single point that was missing. In most of the cases, what happens is, right, so say E is Q, well, just QK over x squared plus y squared. So that's definitely infinity. You can't, there's no way to paper over that. And so electric fields with point charges is where this tends to kind of go screwy. So this actually is one of these little mathematical fine prints that has some physical implications, but I'm hoping to dance around those in this class.
But that wouldn't be something where you even use L'Hopital's in the first place, would it?
Right. So you can L'Hopital your rule, maybe L'Hopital your way out of some things, but you're not going to be able to like
Right.
where this, the situations where this becomes an issue, L'Hopital won't help you. Yeah. Okay. So what I want to do now is think about this construction. Why am I calling it curl? Why does this appear? What does this mean? And I'll do so indirectly. And we're going to end up with like two things for the price of one. We're going to gain some understanding of this algebraic structure, and we're going to gain a new form of the fundamental theorem of calculus. So there's a nice reward at the end of this. And I should mention my derivation is following the book pretty closely in 900, 901, 902. So you don't necessarily need to take notes. Okay, so suppose we wanted to know about this. So here's some C, f dot dr. And I claim that I could break this loop up into a lot of little loops. So let me so the idea is we've got to figure out the circulation around this, and we could do this big long thing going all the way around the edge. Or you could decide, actually, let's divide and conquer. One of us is going to do this tiny little thing. We're just going to, instead of like walking all the way around the pond, I'm just going to do this. And then somebody next to me is going to do this, and somebody next to me is going to do that. And and I claim that if we all did these tiny little experiments and we added up all of our circulations, we would get the total circulation. And here's another way to see that. So suppose I do the circulation in this direction, and then my comrade does the circulation over here. And so maybe I would get a positive number for this part, and my comrade would get a negative number, and they're going to cancel out. So I claim that that's the same as doing this. I'm making no claims to it. This would clearly be an inefficient way of doing things because we're like deliberately double counting things. So this is not efficient, but maybe like a lot of students need work-study jobs. Got to find something for people to do, and there's no snow to shovel, so we have all you'll do this. I don't know. I should also mention, although you probably already suspect this, it's not going to be obvious where this is headed for a while, but it'll be someplace neat at the end. So how do people feel about this? OK, great. So now I want to think about just one of these small circulation around one of these small loops. And then I'll do a whole bunch of stuff, and then I'll say, hey, well, we can add them all up, and we'll get that. OK, so no matter what I do, I'm going to run out of room. Here's y naught. Here is y naught plus delta y. So here's one of these little loops that's somewhere inside the pond that one particular work-study student is charged with determining the circulation around. And I'm going to call this C1, C2, C3, C4. And I'm going to worry first about C1 and C3, and then I'm going to worry about C2 and C4. Because it's addition, I can do it in whatever order I want. Okay. So let's think about this. C1 f dot dr plus C2 f dot dr. And in both of these, for both C1 and C2, I'm moving in the x direction. And I'm moving a distance of delta x. So I claim that dr is going to be delta x I.
You mean C3?
Yes.
When you wrote that?
Oh, here, yeah. Yep, thanks. Okay. Now, the vector field f, we'll use the standard notation. It's going to have an x part and a y part. So let's write that f1i plus f2j dotted into delta x I. f1i plus f2j dotted into delta x I.
You mean to do
Okay. So this is one of these days. I should probably, probably going to lose a lot of minus signs, right? So I'm going to put some here. And it's clear I'm going to also need some surplus 3s, so I'll put those there and see. Okay. And so right now, C1 and C3 are going in opposite directions. And I'm going to account for that in this line by just saying go along curve 1, go along curve 3. All right. So now let's think a little bit about what curve 1 and curve 3 are. So a couple of things. So f2j, when you do the dot product, j dot I goes away. It's only the I part that's in the direction of I. So all right. This is going to be f1. And this is, I'm evaluating this along here. And so this is going to be x y naught dx x x plus delta x. Yes. So okay, so a couple of things happened here. First, I did the dot product, and I got rid of, so that gets rid of this. And then we need to evaluate the vector field along the particular curve. So then I say, okay, well, where is this curve? Aha, this curve is here. So x, sorry, this should be, this isn't x naught, I'm sorry. So along this curve, I'm always at an altitude of y, and x changes. X is a variable. That's what I'm stepping along. Yep. OK, C3. C3, I start at x naught plus delta x, and I go to x naught. I'm going to the left, not to the right. So this is going to be x naught plus delta x to x naught. The dot product's going to work the same. So I and I are fine. I and j give 0. This is f1. What am I going to plug in? Where am I evaluating f1 this time? x and y0 plus delta y, yeah. Because when I traverse back to the left, I'm at a higher y value than I was before, and the field might not be the same there. And I mean, you can already see where this is headed, maybe. If the field is the same there, like maybe there's just like a constant wind in this direction, and you walk this way, it's at your back. You walk this way, it's in your face. It cancels out. On the other hand, if the wind is stronger here than it is there, then these two aren't going to cancel. OK. So now a little bit more. Now the minus signs come in. Let's see. So I'm going to keep this term the same. And I'm going to change the limits here. So an integral from blah to blah is the same as minus integral from blah to blah. And now I have this. Now these limits are the same, and so I can combine this into one big integral. And so if I do that, I'm going to have this whole thing from x0 to x0 plus delta x. We're maybe halfway through, maybe a little bit more. X, y0, that's f1, minus fx y0 plus delta x, no, delta y, dx. So all I did was I just combined these terms. And then I want to do one more thing, and then it'll start getting better. I'm going to factor out a minus sign, just again because I'm in that sort of mood. And it will be helpful. It will be convenient if we factor out a minus sign. This is still f1 minus f1 x y0. OK. Does this term in square brackets remind you of anything? Or even in words, what does it tell you?
It's like, it looks like it's
The numerator of the difference quotient.
Yeah. Finish your.
forgotten what it is. I mean, well, we were just the FTC, the second half of the FTC.
A little bit. So this is.
Or like something slope related.
This is something slope related. Yeah. So this is f1 at y0 plus delta y minus f1 at y0. So this is the difference between f1 at y0 plus delta y and y0. So I'm now going to do the following. I guess I'll do this in. So I'm going to multiply top and bottom by delta y. And then that really looks slope-like, rise over run. So I claim that this whole thing is approximately equal to minus. So this is the partial derivative of f1 with respect to y times a delta y times a dx.
Looks a lot better.
Definitely. And again, you can say, right? Here's a minus f1. Oh, that's just a y, not a y1, sorry. So we can kind of see, that's interesting. So I want to do one other thing. And let's see if you like this. You'll like it because it makes it better, but convincing you that it's legal may be harder. So this is a really small little circle. Or a small little step, because we want these little circulations to be small. And technically, we're going to take the limit. We're not actually going to do it, but that this gets vanishingly small. And so if you have an integral over a really, really tiny interval, and this doesn't change fast compared to the size of the interval, you can replace it. What am I trying to say? Like, pretend this is a constant, because it really almost is. If this was a I don't even know where to do this. If this was a, okay, let me go over here. Oh, I better keep my minus signs because I may need them. Okay, so by the way, suppose we had x naught to x naught plus delta x of 17. What's that? It's going to be, well, 17x. So it's just 17 delta x. And geometrically, so I claim in the limit that delta x gets very small, this sort of nice relationship is true even if we don't have a constant. And so I claim that this whole thing is just going to be minus partial f1 partial y delta x delta y.
How do we know partial f1 partial y to be like convergent that way?
We're assuming that the vector fields are continuous, so they have well-defined derivatives. And so if you think, hey, I don't think this is a good enough approximation, I could say, fine, I can make this approximation as good as you want by letting delta x get as small as you want. So this is not a rigorous proof, but hopefully it's at least somewhat convincing.
How does that not work for, I guess, how does that not work for everything?
It does work for everything. If you integrate over a tiny, tiny interval, you just end up picking out the value of the function. All right, so let's see. I guess I'm going to erase this, but where am I now? So we've shown C1 f dot dr plus C3, I remembered, f dot dr is equal to minus partial f1 partial y delta x delta y. And let me step back and try. Well, let me push forward a few steps, and then we'll step back. Are there any other people feel sort of okay about this? I don't know how I'm even expecting you to answer. Let me, all right, so similarly, C2 f dot dr plus C4 f dot dr equals plus f2 x delta y.
Why is it that term is positive?
Because I don't, let's see. Here, when you're going in the positive x direction, you're at the lower y naught. Here, when you're going in the positive y direction, you're at the higher x naught. So that's going to mean that these terms enter in opposite order here.
Is this contingent on like your orientation, like the direction that you're rotating?
Yes.
So this only works for counterclockwise.
Right, and if you did clockwise, it just introduces a minus sign.
Oh.
So those can be handy. Yeah, so the orientation of the loop matters, unless it's 0, of course. OK, so I think I'm going to erase this stuff, even though I'm sure that as soon as I erase it, I will want it again. But that's OK. Yeah. So what we just found is what one of these work study students would have reported for the circulation about whatever tiny little loop she or he was integrating. So we can now go back to this, right? So the C is f dot dr is sum of the circulation over small loops. And now we have a formula for that. It's f2x minus f1y delta x delta y. So what is this expression on the right look like? So this is the curl, yeah. But what if you have a sum over a delta x delta y? This is, you're adding up a whole bunch of areas. Yeah, so this is actually a two-dimensional integral. So here's what we've just shown. F dot dr is equal to which is Green's theorem. Green chalk, how handy. It'll be a pain in the ass to erase, but it's worth it. OK, so now let's take a couple deep breaths and think about all the different things that this means. OK. So first, just the setup. This notation means we have a closed path C. It's oriented traditionally in a counterclockwise direction. And then R is the region, the area enclosed by this loop. And this says in words that the total circulation around this curve is equal to the total curl of the vector field inside the curve. Here's another sort of an analogy maybe to think about this. So going back to the gradient result. Or this. So in good old-fashioned Calc 2, we have an integral that's about what's happening all along this interval from A to B. And it turns out that we can replace it with a statement about what's going on the boundary of the interval. And the boundary of an interval is just 2 points. Here we have an area integral that's about all the stuff that's going on in this area. But we can replace that with a statement about what's going on the boundary of the region. But in this case, the boundary of the region is a curve and not merely 2 points. So this is a variation, a different form, a vector form of the fundamental theorem of calculus. And we'll get a few more of these over the next week or two. Let's see. Let me now go back to here and try to justify again why this is kind of a curl. And so imagine if you do this, and I sort of said this before, imagine if you do this tiny little loop as part of your work study, and what would have to happen for it not to be 0? Well, the field would have to have different strengths in the x direction for these different y values. And that's exactly what that means. F1 is the x part of the field, and if the x part of the field changes with y, you're going to have probably different numbers here. And or, if the y part of the field, because you're moving in the y direction here and here, but you're at different x values, if the y part of the field changes with x, you'll also have different values here if the y part of the field changes with x. So these terms both contribute to there being a non-zero circulation around a tiny little circle or square at this particular point. And if you add up all of those tiny circulations, which you can imagine thinking of it as a curl, it's not the worst term in the world. So the total curl gives you the total circulation. Let's do a quick example, and then we'll just see what you think. So let me just say a few things about this. Really? Oh, OK. We'll get it in a second. So we now know 2 ways to evaluate this integral. We could parameterize the circle and do a dot product and then a complicated integral in terms of t. Or we could say, well, gee, maybe it would be, because this is closed, so Green's theorem applies, maybe we could actually turn it into an area integral, which most of the time make things worse, right? We're taking one integral, turning it into 2 integrals. This could be an iterated integral. But if we calculate the curl, we get, gee, what do you know? This has a constant of 1. And constants are pretty easy to integrate. The integral of 1 over the area is just the area. I'm just adding up the area. The area of the circle is 9 pi, and so the answer is 1 times 9 pi.
Does that work whenever it's a constant? If it was a constant?
Right, yeah. If this was 17, it would be 17 pi. But if this was x, you would then need to set up the double integral.
Okay.
Yeah.
So do you figure that out just by looking at it and saying, oh, if I do the derivative with respect to the opposite variable, that will give me a constant?
Yeah. I don't know of a... Sorry. Seriously? But it's good, that makes me pay for it, right?
I don't think so.
No, it's gonna...
Oh, yes, now give us your credit card.
Yeah, I don't want to give Steve Wolf my credit card. I don't... This is not a difficult thing I'm asking it to do. Well... There we go, maybe. All right, so this is certainly, if I were to go in a circle around this, whatever is happening here, these arrows are tiny. I'm going to have sort of a big push when I'm going this way. This is 0 because I'm perpendicular. Maybe going to be a little smaller. I don't know. It's not. I find it hard. I find it a little tricky to look at a field and say if it's a curly field or not. But I could imagine. So it is indeed the case. I mean, like, so this arrow is smaller than that arrow. It's a little hard to see, but it is. And so, and this arrow must be a little bit smaller than that one. So if I were, again, the sort of work study student doing a tiny little circulation loop, would get a bigger push in the back here than a push in the face here. So there'd be a little bit of circulation right here. You look somewhat unimpressed. It's OK. So let me see. So this, here's Green's theorem again. This is certainly not something, so like I mentioned last time, like sometimes good math is on the edge between like seeming deep and mysterious and also sort of obvious. This is definitely one of those things, although to me it more often feels deep and mysterious. Like that this turns out to be that, turns out to be that, it's just sort of weird to me. I don't have a gut feeling for, oh yes, of course, it has to be true. Maybe if like this was the only class I taught every term, somehow this would become intuitive to me, but it's still a little bit mysterious. On the other hand, the argument about this is the circulation at a point by going around in that little square rectangle, and if we add up all the little circulations, we get the total circulation. We're like, oh yeah, of course. What else could it be? So again, this doesn't quite feel intuitive, but that derivation, even though I know some of the algebra was there's a lot to write, maybe makes it less mysterious. And this also is the first of what will be several examples where fundamental theorems will be relating not integrals to numbers, oh, of course, that's behind the screen, but one integral to another integral in the lower dimension. So we'll have another form of this where an area integral turns into a line integral, and then we'll have a volume integral turning into a surface integral. OK. Let me see here. How are we doing for time? Yeah.
I don't know if it's not for a question, but because it's a circular integral, does it hold true also for like any closed curve?
Yes.
It's not
Mhm.
curvy?
Yep. So that would be true for a square,
Okay.
rectangle, trapezoid, you name it. Yep. Yep. All right. Does anybody want to stare at this picture any longer? OK. Just because like once I turn it off, it doesn't turn on again for a while. So a little bit of risk in this. OK. Bye. Okay. Let me just power this down. Okay. So that concludes chapter 18, and I think I would like to say just a little bit about chapter 19 to sort of get us starting to think about that, and we'll do chapter 19 in earnest. Start chapter 19 in earnest on Friday. Okay, so. So we've learned about circulation. Okay. All right. So chapter 18 was about line integrals. Or more generically, things like that. And that was a new type of integral. And we now know kind of two ways of thinking about them. One way is to convert it into an integral in terms of time by parameterizing the curve. Straightforward, but not particularly fun or elegant usually. And the way we learned today was we could also think about, well, if we have a circulation set up, we can think about it as being the total curl inside that area. So chapter 19 is about yet another type of integral called a flux integral. So let's talk about flux. So flux is a measure of a flow across a surface. So imagine we have some vector field F. And this could be a lot of different things. This could be wind-driven sleet pelting us horizontally. This could be butterflies flying through the air. Or this also could be electric field lines. And you might want to know how much of F flows through A. No. Actually, this is a cross product in disguise. Of sorts. That'll be next week. So flux measures the rate of flow through a surface. So to do sort of a concrete example, we might have some, like F might be butterflies per second per meter squared. So F could be so the picture here is, imagine we have a whole bunch of butterflies, and this also could be wind or water, but butterflies are fun. So we have a whole bunch of butterflies flying horizontally, and we want to catch them. And if we had a 1 meter square net, this is not square, but actually, so maybe this has, if this says unit of 1 square meter, I mean, okay, it doesn't, but it did. And the butterflies are coming this way, I would put the net like this, and then I would be catching that many butterflies per second. So what I'm doing is I'm taking F times area to get butterflies per second. And those Okay, so again, imagine butterflies streaming left to right. However, what if I chose to orient my butterfly net like this? Then how many butterflies are flowing through my net? None, right. And so, and if it's like this, how many butterflies are flowing through? Like less, right? So, so it's not quite as simple as this, which is why it's in quotes. So the orientation of the area matters as well. It's going to need an angle, yep, and you can just about smell the dot product about to happen. So, so for a surface, we need to like specify a direction for a surface, and the standard thing is to choose a vector that's normal and perpendicular to the surface, and you have a choice which you how you want to orient the surface. You could say, I'm going to choose butterflies flowing this way to be positive, but you could just as well say, actually, I want to count them flowing that way as positive. So there's some choice in how you define what you define as positive flux. So then, flux through surface is going to be F dot AN, which is also sometimes written F dot A. Is that how our book does it? Yep. So I always feel like this notation is weird. Like suddenly area becomes a vector. But if you remember, it's just because if you step back and think, oh, this is in the context of flux, and how I orient the area is going to determine how many butterflies I catch or how many raindrops I catch or something. And so, reminder, this is and that sort of makes sense. This pen that somebody left here says it's an art pen. That's what it says on it. It says art, 88/41. So anyway, this would be the normal to my surface. And so if the normal to my surface is parallel to the field, then that's the maximum way to catch butterflies. If it's perpendicular to the field, that's the minimum way to catch butterflies, i.e. you catch no butterflies. If you did it this way, technically you're catching negative butterflies, which wouldn't make sense in terms of butterflies, but it would make sense in terms of electric field lines. So anyway, I'm trying to suggest that like this cosine makes sense from what you told me, right? And you know how to catch butterflies. You orient the net so that the butterflies fly into it, not into the side. OK. So there is one more complication. And I guess I'll do it here. It seems such a shame to erase Green's theorem, but it's going to, everything's impermanent in the end. So it turns out that butterflies don't always have a constant density. So it could be the case that like there are lots of butterflies here and not so many up there. And so now you hold up your butterfly catching net, and you have lots of butterflies streaming into the bottom. They're coming in at a very fast rate, but they're not coming in so fast at the top. So how do we handle that sort of situation? We're going to do, we're doing an integral by imagining a whole bunch of really small butterfly nets, because we want to add up. We want to know the total number of butterflies flying into the net per second, but the thing we want to add up is changing as we add it up, so that's calls for an integral. So more generally, flux through surface equals sum of flux through small surfaces So the picture here is, I'll say, all right, tiny little butterfly net. Could be another work study job. Tiny little butterfly net, tiny little butterfly net. And if the butterfly nets are sufficiently tiny, then the flux is not going to change over them. So this would be sum of F and, I guess, because it's a tiny little butterfly net now. And that's going to turn into integral over a surface of F dot dA. Let me make sure I'm using the same notation as the book. Yep. Bless you. Let me see. Let's try just one of the problems on the other side of the sheet. Let's try. I lied. Let's try two. Let's try problem A and B. Okay, so here we have butterflies flying, and they're flying with a constant density, sort of like this would be butterfly flux density. 3 in the x direction, 4 in the minus y direction, and 5 in the k direction. And so if we think about the bottom of this cube, the only part of this field that flows through the bottom is the z part. These two parts are perpendicular to this butterfly net. So all I really care about for the bottom is this number 5. And it's constant over the entire bottom of the thing. It's constant everywhere, in fact. And then if I decide to orient this thing outward, so that means I'm going to choose n to be negative k. So then this is going to be, this would be integral, well, f dot k dA. F dot k is just 5. And here we have one of these fun integrals. When you're just integrating a constant, it's the constant times the area, which is 4. Oh, except this was negative k, sorry. Yeah, those are at the bottom, yeah. And what would happen, what's going to happen at the top? Positive. Yeah. Everything's the same except we have a plus k instead of a minus k. And so the z part of the butterfly flux density is constant. So it doesn't depend. When I'm doing it on a given surface, I don't have to worry about it varying horizontally. And if I do it on different surfaces with different altitudes, it's the same thing. OK, so here's what this says in terms of butterflies, which is not anything deep. So imagine you had an imaginary cube. So you weren't actually catching butterflies, but you just had a cube, and you wanted to know how much is flowing through them. And so this says that the amount that flows, the flux through the bottom and the flux through the top, cancel. Which sort of makes sense. I mean, they're just all just flowing right through it. You have as much flowing out of the box as you do flowing into the box. Suppose these numbers were not the same. What would that mean biologically in terms of the butterflies? If if this number was bigger than that's negative, you had a positive number, biologically what's happening? Yeah, or you're making butterflies in the box, however that happens. It's probably bio 1 or bio 2. I don't know. And what if you had less flying out than you had flying in? You're catching them, or they're dying, or they're resting. They're just sleeping. The butterflies are just sleeping. So you can kind of already see where maybe this is one place this is going to be headed, is that if you have like flux through a closed surface tells you how much of the stuff is being made or destroyed inside that surface. And so that's intuitive more or less from butterflies, but we'll come up with a bunch of math for that probably over the next week or something. So we'll do a bunch more with flux integrals. These take some practice, and we're not going to do any really deviously hard ones, but we'll just do some ones with relatively simple integrals to do. So we'll practice that on Friday. And I can stick around here for a minute or two, but I have a faculty meeting 11:10ish.